Hello, salam alaikum. I think we should start. Just tell me if you are ready or not. Okay, Celia is ready. Okay, cool. The presentation is shared, so normally you're seeing the presentation, right? Yes, no? Are you seeing the presentation? Okay, okay, great. Okay, so I think we should start. So hello and welcome to the second session or reading session of School of AI Algiers. We started talking about this paper, a survey of deep learning for scientific discovery, as it was like a long paper, 38 pages. We divided it into in two sessions. So in the first session, if you record, we talked about the whole pipeline of deep learning models, like how we have like 3 stages. The first stage, we talk about the data, we analyze the data, we do the pre-processing, and then the second stage, we choose our model, we select our model, and then we train it. And for the final stage, we validate our model, like testing it in new data, and we analyze it, we interpret it. And for each stage, there are some iterations where we go back. I can show you like, okay, where we go back to the previous stage and we process the data, for example, or we train the model or choose another model, etc. So this we've done it last time. We discussed it, and then we discussed like some algorithms that are in machine learning but not deep learning, and that are useful in some cases where deep learning is not. Dimensionality reduction, clustering, linear and logistic regression, decision trees. Okay, and then we stopped here. We stopped with the CNN applications. So I don't know if I need like to remind you the discussion rules. I don't think so. So we're not going to talk about them. If you need to review them, just go to the YouTube channel and check the previous session, the first session. So maybe someone would like to remind us what are the tasks of CNN. Of course, don't forget, you can speak at any time. This is not a talk. I'm not going like to describe what's going on with the paper, but we're just going to discuss the concepts that are in the paper. So maybe someone would like to refresh our minds and tell us what are the tasks of CNNs described in the paper. Okay, maybe I should describe them myself. Okay, and I hope you'll talk in the other discussions. Okay, so what we talked about is that, so we have image classification. It's the basic task. Like we will have an image of a dog or of balloons, and then just the model will classify it as an image of a dog or an image of a balloon, or it will classify it as in a certain class. And then we have object detection, where we have an image and we ask the model to detect the objects in the image. So for example, here we notice that it detects the balloons. And then we have segmentation. We have 2 types of segmentation. We have the semantic and the instance. In the semantic segmentation, we have like a whole class and we're trying to detect them all. Okay. So we have, for example, balloons, and we say to the model, detect us the balloons, and in the image, we have them all in blue. And then we have instance segmentation, where each individual balloon is an instance, so is separate from the other one. So here we have like multiple colors. It can be like persons. We want to detect all the persons in the image. And these are instance, these are unique individuals that we want to do instance segmentation rather than semantic segmentation. And then we have super resolution, which by its name, it means that we have like some image that is in low resolution format, and we wanna we want an image with a high level of resolution. And then image registration, it means that the model will try to detect if the two images are aligned together. For example, I have like an image of a brain MRI, and I have another image of a brain MRI, but it is rotate. And I want to rotate the other one so that I align it above the first one, so that I can detect maybe deformation or something like this. And then we have pose estimation, and in pose estimation we have an image where, for example, players of basketball are playing, and I want to detect each individual and the pose it is making. So I have like a sticky like a human stick that I can detect the whole body and the pose that it is making. So these are the CNN applications, and we stopped here. Okay, and we stopped here, and now we're gonna like this make the fourth discussion. I know that in the paper they are talking about graph neural networks first. So if you want to discuss graph neural networks, go ahead. Or if you have like a question about the CNN applications. Are you here? Like, do you hear me? Do you have any question about CNNs? Do you have like a question about graph neural networks? Do you want me to speak in Arabic? Do you want me to speak in French? Come on. No questions, apparently. Okay, so if you read like the paragraph they are written, they are writing about graph neural networks. They give just an overview of what are graph neural networks, and they said that some of the data we have are in graph format. For example, for molecules, for chemical products, or something like this. So these are in graph format, and to analyze them or to predict something on them, we need like some graph model that can read the graphs and that can interpret what a vertices is, what an edge is, etc. So this is the global definition of what are the graph neural networks. But like graph neural networks is one of the hottest topic now in deep learning, and I believe that the papers in ICLR, most of them are about graph neural networks or neural architecture search. So this is a very like good topic if you want to start, if you want to have like new ideas in deep learning, etc., and contribute to deep learning in general. So the fourth discussion will be about sequence data. And again, this is not a talk, so I will need you like to present or to talk about what are sequence data, what is language modeling, what is a sequence to sequence. So if someone wants to join in and talk, مرحبا بكم. So we're just starting the discussions, but like discussions need a little interactivity. And okay, so sequence data are basically like text or any like text, videos, audio, sound, speeches, etc. So these are considered sequence data. So the first word will lead to another one, will lead to another one, etc. So language modeling is the first task in NLP, that is natural language processing, that considers the task to predict the next word in a sentence. So for example, I give the model some few words. I give it like, we are in a discussion, and then I let it try to predict the next word in this sentence. Okay, so Malak language modeling, you have the word T and you try to predict the word T+1. Exactly. Just to precise, you don't have only the word T, but you have like multiple words until T, and you want to predict the word T+1. Okay, then sequence to sequence is like the most relevant example of sequence to sequence models are the translation. So the idea is that we have a sequence of words and we want to translate it in another sequence of words that doesn't have like the same length, necessarily have the same length. So in translation, it's the perfect model. Like we have a sentence, and then we want to translate it in French or in Arabic, and then we will have like a shortened, less number of words or less numbers of tokens. So these are the sequence to sequence model. And then we have like another task, which is question answering. And in question answering, the goal is that we have some question and we need our model to learn the answers to these questions. So it's basically like a chatbot, but we want it to be like, these are like more specific chatbots. So maybe a medical chatbot or some customer chatbot, etc. And for to do these tasks, the first model, or the first models that really achieved well performance in these tasks are the RNNs. So the figure here illustrates an RNN or an LSTM to be precise, but the basic of a recurrent neural network. So we have like some cells, and in each cell we have xt is the token. So xt minus 1, xt plus 1. Oops, sorry. And then we have like the previous results of a token is given to the current cell, and we give it also the previous results of all the previous cells. So we have some kind of memory. So this is a high-level overview of an RNN. So we have some cells, and each cell we give it like a word, and then the result of the RNN is given to the next cell, plus the result of all the previous cells past this cell. Did you understand the RNN, or do you have any question about them? At least tell me no so that I can continue, or just give us some other information or something like this. You're free to unmute yourself and talk directly.
سلام هاجر.
وعليكم السلام ورحمة الله.
هاجر هذا LSTM normalement.
Yes, هذا LSTM, mais LSTM it's a cell. تما la structure تاع cell it's an LSTM, mais the whole model is a recurrent neural network. السيل تاع recurrent neural network اللي راك شايفها اللي فيها غير طونجونت هذا كيسموه فانيلا recurrent neural network. Okay. In LSTMs, we have also a forget factor. Yes, we have a forget factor because of the vanishing gradient. I don't want like to enter in too much details because like the paper is just a survey. So I want to talk about the applications and the tasks. more than the technical implementation of each like model. Because I believe that we're going like to have other papers to discuss. So maybe we're gonna have the LSTM paper next, and the Odyssey of LSTM is an awesome paper to start with. So maybe we're gonna have LSTM next. Okay, so if there are no more questions, maybe you can talk about the transformers. The transformers. So the problem with this kind of model, the RNNs, is mostly the vanishing gradient. So it means that if we have like a word, and then we have like a long paragraph, and then we have another word referring to the first word, the problem is that the model won't detect that the second word refers to the first one. So imagine you have like a long sentence, a long paragraph, and then you have some words at the end that refers to the first word of the paragraph. And the model won't like recall that this word is the first word. So it cannot translate it well or analyze it well. So in this with this problem, the solution is the attention mechanism. The attention mechanism helps the model have an idea of all what's happening in the paragraphs before and so that it can like have a long distance relation between two words. And the transformers are the perfect implementation of the attention mechanism. So these are models that implement well the attention mechanism. So I don't know if you heard about like ExcelNet or BERT. So ExcelNet or BERT are based on, so ExcelNet is based on a transformer. BERT is somewhat based on a transformer with some RNN in it. So this is BERT is also another interesting paper to read. So I think here I put some examples that use sequence data models on medical question retrieval, improving the prediction of protein secondary structure in 3 and 8 classes using recurrent neural networks, and BioBird, which is also used for protein understanding and explain and trying to understand the mechanism of any protein. So do you have any question in this section, or should we like go to the discussion number 5? Please don't forget, if you have any question or any additional information, just unmute yourself, interrupt me, just say what you wanted to say. This is a discussion and not a talk. Okay, one example is trigger words. Okay, what are trigger words? To wake up devices. Like okay Google. Okay, like hey Siri, okay Google, etc. Okay. So these are trigger words and are examples of what? There are examples of like sequence data or? Oh, RNNs. So I don't think they are, okay, I don't know how they are like treating the okay Google or hey Siri to start the assistants. I don't know if they are using like an RNN. Maybe.
it's an RNN to detect and to analyze the audio.
Okay, the speech and to detect that it is Hey Siri.
Yeah.
Okay, maybe. Okay. Okay, I think we can like go to the key methods of supervised learning unless you have any question. So I'll start, and if you have any question, just interrupt me. So the first key methods that is described in the paper is transfer learning. And basically transfer learning is when we have like a standard model and then we pre-train it. For example, in any data set, for example, ImageNet is a data set that contains billions of images with more than thousands of classes. So we train it with ImageNet, and then we have those weights. And when we want like to just classify if these images are dogs or cats, we just fine tune the weights with the data set we have. So we don't start with randomly initialized data, but we start with the data weights. Sorry, with randomly initialized weights. We start with weights that are obtained with the training on ImageNet. So this is really useful because the training time will be reduced, and the performance of the model will be better. So basically, this is transfer learning. We pre-train the model on a generic and diverse data set, and then we fine-tune it when we have like the target task. Any question on transfer learning, or should I continue? In transfer learning, change the last layer or maybe more and set the previous layers as non-trainable. Yes. So yes. So what you're saying is that as the classes like diminish, the number of classes diminish. So we have like dogs or cats. We have just 2 classes. So I need the last layer to be just 2 classes, and maybe the fully connected layer. I can add like a fully connected layer, and then I will like set all of the weights of my model, pre-trained model, to non-trainable, which means that they won't be updated during the training, and just the weight of the last layer will be updated. That way I can train my model faster, and I can get like more results, more better results. Okay, so this was transfer learning, and then we have like domain adaptation. In domain adaptation, what we have is that we have two data sets. We have the source domain and the target domain, and we have like our model. Our model will be trained on a source domain, and then we want it to work on a target domain. For example, the example they give on the paper is that we have like handwritten digits, and we want to train it on the mnist handwritten digits, but then we want to apply our model for the numbers of the houses in the streets. So these are two different data sets, but we need like to have, we can work with the same model to detect the numbers on the handwritten digits data sets and on the house numbering data sets. So with domain adaptation, we adapt our model so that it can detect even the house numbers while being trained on handwritten digits. With multitask learning is another approach where we have, like, for example, a medical image, and we don't want to just predict a disease, but we wanted to predict the disease, the patient age, the history of other related diseases, etc. So this is really beneficial if we want to check our model. And the idea is that what we have is we have multiple output layers. So we have the first output layers for the disease, and then the second one for the patient age, and then the third one for the history, etc. And we train the model for these for these three output layers. So this is multitask learning. Okay. And then we have weak supervision. In weak supervision, what we have is that we can have like some data sets. We can, when we collect like the data, we can have some cases where we cannot get the correct labeled, the certain labels, but we can like have some noisy labels that might be relatively easy to collect. So with weak supervision, we are training a model on a data set with these noisy labels. So for example, they give like, I think they give an image application of the weak supervision, where we can have like a model that classify the image on for example, dog or cat, and then we want to create a segmentation, so a pixel level labels, by inferring the pixel level labels on the image classification by the image classification model. We can have also a weak supervision by having like an image classification on Instagram and using the classes as the tags of Instagram. So the tags are relatively not certain to be what is on the image, but we use them as weak supervision to like train our model in a supervised learning way. Okay, I think I finished with the key methods, but do you have any any idea to add, any additional information or any question, or should I like explain more some of the concepts here?
Hajar.
Yes.
In domain adaptation, we use the first network that we get from the first domain as an initial initiation for the network for the second domain, or we don't retrain it again.
No, we don't retrain it again, because if we train it again, I think it's transfer learning.
Okay.
Right?
Yeah.
So what do you mean is that we have like a model, and then we have we train it ننطرينيوه على الفيرست داتا sets، ومن بعد نحكموه ونعاودوا برك ننطرينيوه على السكوند. هذه هذا واش حابب تقول؟
In this case, it's transfer.
هي ماشي هكا تصرا. هي واش يصرا سيك نونطرينيو لو موديل تاعنا على الاولى ومن بعداك نسيو نبدلو سوا لي ويتس سوا لي زيماج تاع الهاوس باش نرجعوهم يشبهوا لي زيماج تاع الهاند ريتن فور اكزامبل.
صح يكون لو ميم
دونك
بروبليم.
كي نجي نبدل لي ويتس هادوك بيان سور يكون لو ميم بروبليم زعما راني نسيي نديتيكتي لي نومبر راني نسيي نديتيكتي لي شيفر.
داكور.
استنى كنت سور من روحك على باليش اذا فهمتك بيان.
اها سي بون كي ريبونديتي.
سير. اوكي. اوكي معليش اذا نروحوا لا ديسكسيون 6 ولا عندكم دي كيسيون؟ Okay, so I will continue. I hope you're understanding. Okay. So, discussion 6, we're going to talk about doing more with less data. So the problem with supervised learning is that we need a lot of data to train our model and to obtain significant results. So there are some concepts or some ideas that helps us reduce the number of data that we need to train our models. So the first one is self-supervised learning. In self-supervised learning, we're trying to create the labels ourselves. So for example, we can rotate, I don't know if you recall the image registration task. So for example, we can rotate an image by a certain degree and then create a model that tries to predict this degree. So if you see, like here we have unlabeled data instances, we have some images, and then the image of the volcano is flipped like 180 degrees. And then we have our model that is trying to predict by how much our image has been rotated. So this is for images, for example. We can apply different transformation. We can blur the image. We can flip it. We can rotate it. We can do some transformations on the image, and then we try to predict which transformation were done on the image. For sequence data, self-supervised learning is used a lot. Like in language modeling is itself a self-supervised task. For example, we have a sentence and then we're trying to predict the next word. So we just omit this word, and this is self-supervised learning. So the label is the next word. Okay. Sorry. Do you understand self-supervised learning? Yes. Okay, cool. So there's another method which is semi-supervised learning. In semi-supervised learning, the problem is that we have some data that are labeled and some others that aren't. So how can I do the supervised training? So the first idea is that I will go and use self-supervised learning to label the unlabeled data. So basically, I will have like, I will try to find a way or a natural way to use self-supervised task to get the labeled of the unlabeled data, and then I combine them with the labeled data and get and train my model in a supervised way. So there is another method which is self-training. In self-training, I train a model on the labeled data by a supervised training, and then I will infer from this model the labels of the unlabeled data. So I will first train my model on the labeled data, and then I will try to get with this model the unlabeled data, and then I will retrain my model with the whole data, the whole labeled data. Is this do you understand this one? So the self-training one. Okay. Okay, good. If you don't understand something, just interrupt me, please. Yet, but the risk is high. Yes, really high, because the model, and it depends also on the number of labeled data I have. Yep. Okay, and then we have enforcing consistency. The idea of enforcing consistency is that if a human was given two images, A and B, with B slightly blurred, for example, the human will just say that A looks like B, so I will give them the same label. So we're trying to do the same thing. We're trying to find a similar data as the unlabeled data and give them the same label. So we have some labeled data and we have some unlabeled data, and then we go through the unlabeled data and try to find a similar data, a somewhat consistent data with the labeled one, and then I will give it just directly the labeled one. Okay, so this is enforcing consistency. And then we have code training, similar to enforcing consistency. So what we want is that we want to have this. What we want is that we want to have many models that are trained on the labeled data, and then we want them to have like to predict the label of the unlabeled data, and the highest predicted class will be the class of the unlabeled data. Okay. I don't know if I explained it well. So if you don't understand, please let me know. The risk is even more. Okay. Maybe if we have like maybe if we have like more trained model, so it means that more trained model are sure that this unlabeled data is in this category. So we're trying to reduce this risk. We're trying to reduce the risk. Do you have any question? Or should we talk about data augmentation? So, okay, I think the best solution is the last one, data augmentation. Okay, I think data augmentation is used a lot, especially with images. So, okay, I think we're going to talk about data augmentation. Okay, so data augmentation is when I will try to explain it with images and then explain it with sequential data as well. So with images, when I have like an image of a dog, I can add multiple image of dogs by trying to put some transformation on this image. So we'll have like some rotated dog, some blurred dog, or with other colors, or center crop or something like this. So I will apply some transformations to add the number of images in the data set. So basically, this is data augmentation. And then for sequence data, so either we're directly modifying the input sequence, or in the case of sequence to sequence tasks, we are increasing the number of input output sequences by a noisy translation with the neural network. So for example, one direct example for sequential data is using synonyms. So we can like replace a token with its synonym, so that I can add multiple data to my model. Okay, do you have like some additional information here, or question if you would like? If you didn't understand something, please let me know. There's also another example for data augmentation in sequence-to-sequence model. Like, for example, in translation, we're trying to translate from English to French, for example, or from English to Arabic. And then we'll have like, we can like have a translation. We try to translate a sentence to Arabic, and then we have like this pair. This sentence is translated to this sentence in Arabic, and then we can use like Google Translate and translate the sentence in Arabic using Google Translate to English, and then we can have like another pair of sentence. I don't know if you understand this. Yeah, okay, you understood it. Okay. So basically, we're not going to use like Google Translate, but we're going to use some API that is going to make things faster or something like this. But this is the example. Exactly. We want to express the same thing with different sentences or with different words, so that our model will learn more. Okay, I think we can go to the 7th discussion, which is interpretability. Okay, this one is a tricky concept. So the problem with scientific discovery is that we don't want to predict only. We want to understand the phenomenon. So, for example, they gave a good example. They said the core. Okay, so So the core scientific question might be on how certain amino acid sequences give rise to particular kinds of protein functions. So we want to understand how an amino acid sequence can give rise to a certain kind of protein. But using deep learning, what we're going to do is that we're going to make a model that will predict the output or the properties of the protein based on the amino acid sequence. So this is like a problem. I need to interpret the deep learning model and to know how it is going to predict the properties rather than just knowing which properties it is predicting. Okay. So to answer these questions, there are two types of interpretability. So we have like the feature attribution and the model inspection. In the feature attribution, we're looking at what are the features that are the most important to our model, or which parts of an input image are most important for a particular model prediction. And for this approach, or for this category, we have like two methods. We have the saliency maps and input maps, and we have the feature ablations. So the saliency map is when we trained our model. So we're done with the model. We take the weights and we put them with the output weights, and we put them as a mask on the input image. That way we can like get a clear idea on which part of the image is most relevant or is most used by the model. Another idea is feature ablation, and with feature ablation we dropped certain parts of the image or certain features, and we see the impact on the model, and this way we can detect which features are more important. Do you have any question on the feature attribution part or interpretability as a whole? You didn't understand the goal or something like this? Do you have any question? If no, I can continue. If okay, no. Okay, and then we have like model inspection. In model inspection, the focus is on gaining insights not on a single input example level for the feature attribution, but using a set of examples, we want to understand the properties, the salient properties of the data. So here there are multiple methods that are trying to examine the hidden representation of the neural networks and trying to reveal some structures or some learned representations. So we can use like dimensionality reduction on the hidden representation to try and analyze the single cell data. And we can, of course, compare the representations. Like we can have multiple inferences and then compare the representation. So we can like have multiple images of dogs, and then we infer these images. We infer their class through the model, and then we see the representation of the hidden layers and try to compare them with each other so that we can understand which neuron is firing, why is it firing, etc. So if this input is high, then this neuron will fire, etc. So I think this is all for the discussion 7. I don't know if you have any question regarding this. Maybe we can go in details in future papers. It will be interesting to talk about the interpretability. But I think there are a lot of concepts that are interesting for now. So, okay. Just tell me if you have any question or not to go to the discussion. Okay, no, okay. So the last discussion for this paper will be about advanced methods. And we're gonna talk about GANs. I don't know if you heard about them. Have anyone heard about them? Never? Okay, no, okay. So I think you've heard about this application where they are generating human faces. So these images are not real. None of these people exist. So these are generated with a model of a type GAN. So GAN is a generative model. So generative adversarial networks. Okay, so basically the structure of a GAN, you can like divide it into neural networks. We have a generator and we have a discriminator. So the goal of this generator is to generate, for example, human faces, and the goal of the discriminator is to detect whether the image is a human face, is a real human face, or a generated human face. So in GANs, to sum up, we have two neural networks. The first one is generating faces, and the second one is checking whether the input image is a real human face or a generated human face. So the second one, the discriminator, will try to teach the generator how to generate, and the generator is trying to fool the discriminator by giving it some real generated human faces. So, okay. So do you understand like the overall concept? Yes, Maqbal. Okay. Mohammed, est-ce que فهمت? Est-ce que عندك question? Yes, but it needs a lot of data to check if the face exists. Yes, but the images of faces are available. Like, I think this is an easy data set to collect. You may say that it's not private or something like this, but it's an easy data set to collect. Okay, some may wonder like about the dangers of this model, because if we want like to generate human faces, it's something like really weird. We want to create some fake accounts or something like this. A similar task is generating sounds. Yes, there are a lot of works around generating music or something like this. Yep. So we can use also GANs in this task. Okay, another advanced method they talk about. So they talk about the generative models. So there is also another type of generative model, which is the variational autoencoders. I'm not going to talk about it. So there is another advanced method in deep learning, which is reinforcement learning. And I'm sure you heard about reinforcement learning. So if you don't like, if you didn't, maybe we do a workshop to implement this model. Yes, we could. Yes, I prepared a workshop for this for last year WTM. So it's already prepared, and maybe I can share it with you directly so that you can see the implementation of the model. But making a workshop, it's better. Okay. So the other advanced method they are talking about in the paper is reinforcement learning. I'm sure you've heard of reinforcement learning. Like, if you didn't see I don't know if you've watched the documentary of DeepMind with AlphaGo beating Lisa Doll. It's the best. Okay, it's the best documentary I've seen on artificial intelligence and how a machine can beat a human. It was amazing. Okay, yes. Okay, yes. Okay, cool. So, okay, so basically reinforcement learning, it is like how we teach kids to learn things or to prevent them from doing things. So we let the agent try to do something, and then based on the action it made, we give it a reward with or a punishment. So the reward can be like negative or positive. So we can give it a high reward or a very low reward. And a high reward means that, okay, this action is really good at this time. And then a low reward means, okay, this is not a good thing to do, and this has reduced the score or something like this. So basically, this is reinforcement learning, and it is used a lot in scientific discovery. So it was used in robotics, of course, and then there are some. Okay, so I forgot, but there are something about astronomy, chemistry, physics. I think climate modeling was one of the tasks that are using reinforcement learning. And then there are also reinforcement learning for self-driving cars, as Mohammed said, and simulators. Yep. Okay, so this is about reinforcement learning. Okay, so I think we're done with this paper. So maybe if you have any question, just ask it now. For the implementation tips, it's a really, really important part of the paper. I really recommend you to read it. Okay, I don't think it needs to be discussed. There are just some tips that you need to read and you need to follow along while implementing your models. So I think we're done. So if you have any question, ask it. Or if you have any, yes, a homework. Yeah, you have a homework, which is reading the implementation tips. Okay, so I think we're done. So if you have any question, just ask it now. If you have any additional information, ask it also. Maybe we're gonna send a poll tomorrow to choose the next article we're gonna read for next Friday. I don't know if you have any recommendation for papers. So if you have one, just give us the link to the paper, and by sending it on a Facebook message or an email or any social media that you're using, just send us, okay, we want this paper, I want this paper, and we can add it to the poll so that everyone can try to decide which paper we can read. Also, I don't know if the time is from 7 p.m. is good for you or not, because today we're like really few here. So I don't know if the time is not good for you. So let me know in the chat if the time is not good. We can fix another time. Maybe the day. Okay, maybe. Just give me your, like, maybe we can send a form. Okay, we can send a form just to get when you're free and the day and the time you're free.
هاجر.
Okay, for the one. Yes.
هاجر وش رايك المره الجايه نقرا واحده من البيبرز اللي تقدر تعاوننا في لي بروجي باش يقراها.
Which projects?
n'importe quel projet من لي بروجي اللي عندنا هذوك.
Are you all members of School of AI Algiers? Intern project. Okay, it's محمد تاني mom of School of AI. Okay, ما كنتش على بالي. Okay, I don't know. Maybe we can do something like this. Yes. Maybe we can maybe you can make in the poll some papers that are related to the projects, but not really, because we're just starting, and maybe we can like start with اوكي لو كان نديرو LSTM مليحه لكاع لي بروجي باسكو راهم يديروا NLP و it's a good start. اوكي نخمم لهم البيبرز ونحطوهم ونشوفوا واش يخيروا. محمد راهو حايب LSTM وفيك حضر لي دو سيونس دونك راح ينديروا LSTM. Okay, I think we're done with this session. Okay. اوكي يعطيكم صحة. La prochaine fois, Inch'Allah. Demain, نبعثوا البول تاع le choix du projet de l'article. Ok, صحة.